Hello everybody, welcome back to my YouTube channel. Today we will be expanding more on the ideas of neural networks, but today more specifically backpropagation. So what we're going to use to talk about today's idea of backpropagation will be the 3 blue, 1 brown article on neural networks, the 3 blue, 1 brown video on backpropagation step by step, and then lastly, again by 3 blue 1 brown, we will be talking about the video large language models explained briefly. So first we are examining a neural network that is designed for handwritten digit classification, which is something that we've covered in previous videos. While this idea is not exactly cutting edge, it serves as a useful example for understanding core neural network concepts. The network has 2 hidden layers with 16 neurons each, primarily for illustrative purposes. It achieves about 96% accuracy on new images, which can be improved to 98% with modifications to the hidden layers. Again, stuff that we've talked about before. However, model networks can reach 99.75% accuracy, and the key takeaway of this is that the network learns to classify digits without explicit instructions on which patterns to identify. First, it was assumed that the second hidden layer would detect small edges, while the third layer would recognize digit subcomponents like loops. However, when visualizing the weights connected to the first and second layers, the patterns appear almost random. Instead of clearly defined edges, the neurons in the second layer respond more to general blobby shapes. The network has found a local minimum in this vast space of possible weights and biases, which allow it to classify images but does not lead to general pattern recognition. The network's training environment is highly constrained. It is trained only on clearly defined, properly sized, and centered digits. It usually fails when presented with random noise, confidently misclassifying it as a digit. It also struggles with digits that are off-center or not the correct size. The algorithm does not allow for knowledge transfer, meaning the network cannot make any inferences about scaling or pixel adjacency. Visualizing the weight grids of the second layer neurons reveals the blobby shapes to which they respond. By watching the weights change as a digit is drawn, one can gain insight into how neuron activation evolves. This network, though outdated, serves as a foundation for understanding more complex models such as convolutional neural networks, which can learn more flexible patterns. The network's lack of true intelligence highlights the necessity of more advanced models to achieve robust pattern recognition. Though, despite its limitations, it demonstrates how a neural network can learn from data and improve through optimization techniques like backpropagation. Backpropagation is the algorithm that allows neural networks to learn by adjusting their weights and biases to minimize a cost function. The cost function quantifies how well the network is performing by averaging the squared differences between the network's predictions and the actual outputs. The algorithm applies gradient descent, computing the negative gradient of the cost function to determine how weights and biases should be adjusted for optimal learning. And this is a topic that we should all be familiar with, especially after the previous video. The magnitude of each gradient component indicates the sensitivity of the cost function to changes in specific weights and biases. Each training example influences weight and bias adjustments. The output layer's adjustments are based on the difference between the desired and current outputs, strengthening the activation of the correct neuron while suppressing the others. A neuron's activation can be increased by increasing its bias, modifying its weights, or changing the activation of the previous layer. The most significant weight changes occur in the connections involving the most active neurons, a concept loosely related to Hebbian learning. Desired adjustments are propagated backward through the network. Each output neuron has its own desire for changes in the previous layer, and these desires are combined and recursively applied to all layers. To improve efficiency, training examples are grouped into mini batches, allowing the network to perform gradient descent updates iteratively, a technique known as stochastic gradient descent. Backpropagation calculates how each training example would adjust weights and biases for the fastest reduction in cost. By iterating through the mini batches, the network gradually converges toward an optimal set of parameters. However, backpropagation requires large amounts of training data to function effectively. The MNIST database serves as an example of a well-structured dataset suitable for training neural networks. While this method is effective, it does have its limitations, particularly in its reliance on labeled data and the risk of getting stuck in local minima. More advanced techniques, such as adaptive learning rates or second-order optimization methods, can help improve training efficiency and convergence. Now, large language models, or LLMs, are advanced neural networks that predict the probability of the next word in a given text. They form the foundation of modern chatbots by generating words sequentially based on learned probabilities. LLMs are trained on vast amounts of text from the internet and contains hundreds of billions of parameters. These parameters are initially random, but are refined using backpropagation to improve word prediction accuracy. Training LLMs require immense computational power, made possible by specialized GPUs and large-scale processing systems. The first stage, known as pre-training, focuses on auto-completing text, while reinforcement learning with human feedback further refines the model. Human reviewers flag incorrect or unhelpful responses, enabling additional optimization. Unlike traditional neural networks, which are designed for specific tasks like digit classification, LLMs have a broader scope and can generate contextually relevant text across a wide range of topics. Early language models processed text one word at a time, but transformers revolutionized the field by allowing words to be processed in parallel. Each word is converted into a numerical representation, enabling the model to analyze context more effectively. Transformers rely on an attention mechanism, which allows them to determine the significance of different words in a sentence by considering relationships across the text. Additionally, feed-forward neural networks store supplementary patterns, enhancing the model's ability to generate coherent responses. The attention mechanism enables LLMs to capture complex dependencies in language, making them more effective than the previous models that relied on simpler statistical methods. However, despite their advances, LLMs still have some limitations. They do not truly understand the language. Instead, they generate text based on learned statistical patterns. The specific behavior of LLMs is an emergent phenomena arising from their training process, making it difficult to pinpoint exactly why a certain word was predicted. This lack of interpretability raises concerns about bias and misinformation, as the models reflect the data they were trained on. Moreover, their reliance on vast computational resources makes them expensive to develop and deploy. Despite these challenges, LLMs demonstrate the power of large-scale machine learning and natural language processing. Their ability to generate fluent, contextually relevant text has led to their widespread adoption in applications ranging from chatbots to automated content creation. As research continues, improvements in efficiency, interpretability, and alignment with human values will be key areas of focus in the development of next-generation language models. While LLMs have significantly advanced natural language processing, their limitations highlight the need for ongoing research and refinement. One major challenge is their inability to generalize beyond their training data in a truly human-like way. Because they rely on statistical patterns rather than genuine comprehension, they can sometimes generate misleading or incorrect information with high confidence. This issue, often referred to as hallucination, underscores the importance of careful deployment and fact-checking when using these models in critical applications such as legal, medical, or financial domains. Additionally, ethical concerns surrounding bias in training data continues to be a topic of discussion. Since LLMs learn from vast amounts of human-written text, they can unintentionally replicate and amplify existing societal biases, necessitating robust mitigation strategies. Despite these challenges, the progress in deep learning and artificial intelligence has opened doors to remarkable applications across industries. From personalized assistants to real-time language translation and code generation, neural networks and large-scale models continue to push the boundaries of what machines can accomplish. However, as these systems continue to be more integrated into everyday life, balancing innovation with responsibility becomes crucial. Researchers are exploring methods to make these models more interpretable, fair, and efficient while reducing their environmental impact. As machine learning evolves, the focus will likely shift towards developing more adaptable and trustworthy AI systems that go beyond statistical prediction to incorporate elements of reasoning, contextual awareness, and human-aligned decision-making. Thank you so much for watching my YouTube video, and I will see you all next week.